because mercury has some serious health problems associated with it, they don't like people playing with mercury. Now, I can remember when I was a kid, we had mercury all the time. We would go break thermometers on purpose, pour the mercury out and collect it, have a little glob of mercury in a dish and let it roll around and play with it and put our hands in it and pick it up because it was really fun. And you know Alice in Wonderland? You know that? The Mad Hatter? No, the brim of his hat's not made out of mercury. They use mercury in the felting process. Yeah, it's not that the brim, his hat was not made of mercury. He would have a liquid hat, right? The Mad Hatter, he didn't just wear a hat. A hatter is a person who makes hats. And so in the felting process for making hats, that they would be exposed regularly to mercury. And it has some brain effects, okay? It causes some brain damage. And so that's why the Mad Hatter, mad at that time meant crazy. So the mad, crazy, not angry, okay? It meant crazy. So they would be exposed to fairly large levels of mercury. It's what? Toss pennies at mercury? I don't know. You think if we filled a dish, we could try that? Is that what you're suggesting? We do have some. So you're saying if I fill a dish with mercury and I toss a penny at it, it'll bounce? I've never heard that. But now I'm curious. Of course, it'd be completely inappropriate to go into the stockroom and get the mercury and try that. So. Yeah, they wouldn't like that for safety. Our safety coordinator would have a fit if I had all of you doing that. But I'll have to ask. Or you know what? I wonder if we Googled that, if we can see a video of that or something. Maybe I'll have to try that tonight. Okay, so what we're going to look at is how we deal with not using mercury anymore. And the way we deal with it is to look at the relationship between the height of some other liquid compared to the height of a mercury column, and then we can convert to millimeters of mercury and then use that to add on. So we know that pressure is equal to the height times the density times the gravitational constant. And this gets really involved. This is in your textbook. We are going to not deal with this. For our purposes, we're going to combine this to a very simple relationship where we compare other liquids to mercury. So the height of B divided by the height of A is equal to the density of A over the density of B. The height of the column is inversely proportional to the density of the liquid. And that includes the gravitational force. But if you're doing your experiment here, the gravitational force is the same right here for mercury and the other liquid. So we don't need to throw that in, right? So let's look at a typical example. When the atmospheric pressure was 745 millimeters of mercury, a liquid with a density of 0.854 grams per milliliter was used in an open-end manometer to measure gas pressure. The liquid level in the open arm was 17.55 millimeters higher than the arm close to the gas. What is the pressure of the gas? Well, this is kind of a complicated problem because it includes two things. It includes using an open-end manometer, and it includes changing to mercury. So, what do we know? We know the atmospheric pressure is 745.0 millimeters of mercury. We know that, and we'll use that to add in later or subtract. And now I like to draw this so I can envision this for myself. It says the liquid in the open arm was higher than the other one. So the difference here is 17.5 millimeters of liquid. That liquid is not mercury. But regardless of what the liquid is, who's pushing harder? The gas is pushing harder. So the pressure of the gas will be equal to 745.0 millimeters of mercury plus the difference, but I need to convert the difference into units of millimeters of mercury. Right now, that difference is 17.5 millimeters of liquid. We don't know what the liquid is, but it's not mercury. So we have to do a little bit of data collecting. The density of the mercury, we'd have to go look that up. It's 13.6 grams per mil. The density of our unknown liquid is 0.854 grams per mil. The height of the mercury column is our unknown. We don't know how tall mercury would be under these conditions. And the height of our liquid column is 17.5 millimeters. So we know that the height of the mercury divided by the height of the liquid is equal to the density of the mercury divided by the density of the liquid. And I want to solve for the height of my mercury column. Now, I know most of you just kind of like to plug in the numbers first, and that's fine. So the height of the mercury is our unknown, divided by 17.5 millimeters of our liquid. It's equal to the density of mercury, 13.6 grams per milliliter, divided by the density of the liquid, 0.854 grams per milliliter. So now we can cross multiply and solve, and the height of the mercury is equal to 1.10 millimeter of mercury. So that's 1/17 of the height of this other liquid. So you can see why it's inconvenient to use other liquids. Mercury has such a high density that it takes a lot of pressure to make a little change. And so we work with a 760 millimeter column at sea level. So now the pressure of the gas is equal to 745.0 millimeters of mercury plus 1.10 millimeters of mercury. So the pressure of the gas is equal to 746.1 millimeters of mercury. So we had kind of a two-for problem in there. We had an open-end manometer problem plus a liquid of different density problem. So now you're going to do a problem comparing water to mercury. Assume this has 3 sig figs. And do you all know the density of water, which I assume you would know at this point in time? It's 1.00 grams per mil. So go ahead and do that one on the boards.